So yeah, today I'm going to be talking about the harsh truths of interoperability, and some asterisks there because some of them aren't that harsh. Some of them I think we'll all agree with, and truths, some of them are just my opinions. But yeah, let's get started. So first, how are we going to define interop? And for this presentation, I'm going to use this definition, which is the ability to bridge assets between any two chains in less than 3 slots of the slower chain. So this definition came from the interop forum from Vitalik at DevCon last year. And this doesn't cover all interop, but it covers like 90% of the use cases, which are asset bridging. All right, but there's kind of some questions about this definition. So are we requiring trust minimized bridging? Is that a requirement? Do we need to require fungible and non-fungible tokens to be bridged? And do we really mean any chain or just popular chains? So yeah, this is what we're going to use for our definition here. And what I'm going to argue is that yes, all of these should be included in the definition of interoperability. So first, today we use the L1 for bridging. That's one way we do things. And so let's evaluate how does the L1 actually work for bridging and is it useful? So of course, it's too slow. This is what everybody says. L1 doesn't solve everything. I think this one's pretty obvious and everybody would agree with it. But let's actually look into what the L1 is doing and like what the function of it is when you're bridging. So Rollup A wants to bridge to Rollup B. What they do is they settle to the L1, then you can withdraw funds, and then the B will deposit those funds. But it has to go through the L1 first, and this is slow. So what actually is the L1 doing here? So normally we talk at that, it's settlement, and I'm actually going to argue that it's not settlement. It's confirmation. So settlement is really about the bridging. It's really about taking funds out of a rollup and putting them into the L1. You don't actually have to do that if you want to bridge between A and B. All you need is a confirmation of rollup A's state that says, yes, I am bridging these funds. That's all you need. And that's what the L1 is actually doing. It's not settling, it's confirming the state of rollup A. So well, why do we do this? Why do we go through the L1? Fundamentally, it's because rollup B doesn't trust rollup A. So they aren't going to trust rollup A to say, oh yeah, I burned X amount of tokens, but they will trust the L1. So rollup B trusts the L1's confirmation of rollup A's state. And this will become important later on. So, okay, the L1 doesn't solve anything, but how does it do with this definition? So fungible and non-fungible assets, yeah, it works because you can do native bridging on the L1. So totally works. It could be used to bridge NFTs if people wanted to. Bridge between any two chains. If we, say we're only talking about like L2s, L3s that all eventually settle down to Ethereum, yeah, it can bridge between any two chains because all of those chains must fundamentally trust Ethereum. Can it do it in 3 slots or less of the slower chain? No. So this is where it doesn't work out. And is it trust minimized? Yes, because the L1 is about as trust minimized as we can get. So, all right, it has 3 out of 4. That's not bad, but the speed is really, really the problem, isn't it? So, all right, we have intents. And let's see, maybe intents can solve interop. And intents are great because they're super, super fast, which is exactly what the L1 can't do. So let's look at what happens with intents. So you aren't actually going through the L1 anymore at all. A solver basically can read state from rollup A and say, okay, a user deposited funds, and then they will front the user funds on chain B. So the solver must do a couple of things here. One is that they have to keep liquidity on the destination chain. So if we wanted to get really pedantic, we could argue about what is the definition of bridging. And you could argue that actually intents is not bridging because you're not actually moving anything. But this requires that the solver has to keep liquidity on the destination chain, and they also need to rely on a non-intent bridge service for settlement. So this is the really key thing about intents is that you have to couple intents with some other form of interoperability for settlement. So you could imagine that if I'm a solver and I need to rebalance my liquidity or settle my intent, I can't use another intent solver to do that. I have to use some form of like a native bridge. All right, so intents. And I want to point out this is that both of these actually need confirmations. So we have the confirmation ideas coming back up. When the solver when the solver reads the user's transaction on A, it needs a confirmation from A that like that state is actually true. Usually it's just going to listen to the centralized sequencer of A. That's what it usually does, but that's a confirmation nonetheless. And then over here, it needs a confirmation for settlement because you're doing the same thing. You need to confirm some state on rollup B. So in this case, you need to confirm the state on rollup B that the solver actually gave the user their funds. You need to prove that on rollup A. So you also need some form of a confirmation for this, like something that tells you what is the state. And okay, I've been using this term confirmation a lot, and so here's what I'm going to define it as. It provides an end user with information about the state of a rollup. And a confirmation is always based on some assumption. So for example, these aren't in any particular order, but we have some common confirmations. We have a sequencer confirmation, sometimes known as a pre-conf. This relies on the sequencer being honest or potentially some economic stake that they can be slashed with. We have a BFT confirmation. This relies on the BFT network being honest. We have L1 block depth. Say, okay, Ethereum's not going to reorg after 6 blocks, so you're relying on the Ethereum validators to, in fact, not reorg. You have L1 finality, which is have an honest majority of L1 validators. You have settlement, which actually relies on L1 finality, but also has to assume that the proof system doesn't have any bugs in it. And then you have no confirmation at all, which is basically just social consensus. So the question is, which one are we going to trust? We have all of these, and they all have very different assumptions behind them. So okay, let's go back to our intents. So we need a confirmation, and we defined what a confirmation is. Well, intents don't solve everything. So let's look at how this does with our definition. Fungible assets. No, intents can't do fungible assets, or non-fungible assets, because they need liquidity on each chain. And the definition of a non-fungible asset is that you can't have liquidity for it. So like bridging NFTs cannot work through an intent protocol. Bridge between any 2 chains. I'm also going to say that that's a no, because the solvers have to deploy liquidity on each chain. They don't necessarily do that day one. They do it for chains that are profitable to put liquidity on. So you definitely can't bridge between any 2 chains in the Ethereum ecosystem. Less than 3 slots of the slower chain, yes, that's very true. Trust minimized. This one's a little nuanced, but I'm going to say yes from the user's point of view. From the user's point of view, they can't lose their funds. The solver might have other trust assumptions, but for the user, it's okay. All right, so intents don't solve everything. What about base sequencing? We're kind of going through all of the buzzwords. Base sequencing is L1 aligned. We get this synchronous composability between the L1 and L2s. Great. All right, let's see if base sequencing solves interop. So the way base sequencing works is that the L1 proposer is the proposer for the rollup itself. And a base rollup block is always sequenced as call data or blobs, and its finality is the finality of the L1. So it is using the L1's consensus mechanism for finality. And so this requires that it has to reorg with Ethereum state. So if the latest block reorgs for some reason, a base rollup has to also reorg. Problem is that a lot of other rollups don't do this, and they don't do this on purpose because they want their state to have when their sequencer is giving a confirmation to a user, they want that to be very strong, and if you all of a sudden have to be like, well, this confirmation is only as good as if, how often Ethereum reorgs, then that's really not very strong and you're not gaining much. So a lot of other rollups, most other rollups I would say today, they do not want to reorg with the L1. So here I'm going to have I haven't been pointing these out, but these numbered ones are the harsh takes. Is base sequencing is actually just another cluster, a rollup cluster, like the superchain or anything else. And this doesn't mean that it's bad, at all. It's just we should recognize it's a cluster and it can't interoperate with other rollups very well. And in this case, based rollups are using the L1 for confirmation. So base sequencing doesn't solve everything. That's our fifth harsh truth. And let's look through here. So fungible assets, yeah, because you can do native bridging. You know, between any two chains, we'll know because, yes, you can. See, actually, this is why I put this right here, is that it gets hard to categorize these because it depends on the trust assumptions. So if you're willing to trust a sequencer pre-confirmation, sure, you can bridge with the based rollup between any two chains, but maybe that's not what you want to trust. Can it be in 3 slots of the slower chain? No, because of L1 finality. You have to wait 15 minutes for finality, and that is a lot slower than 12 seconds. And is it trust minimized? Well, you could argue yes, because Ethereum is backing it. Okay, so base sequencing doesn't work. TEEs, they can solve everything. They're fast and secure. Awesome. Okay, so we have a couple of ideas. We have sequencers run in a TEE. Maybe this makes our sequencer confirmation a lot stronger. So now we can use it for interoperability. So we can say, hey, instead of waiting for the state to finalize on the L1, I'll just trust the sequencer's confirmation of state. And you know, TEEs are also good because they enforce certain ordering rules, all of these things. The key part is, though, it actually doesn't get you a whole lot because the sequencer can still equivocate and censor. The TEE does not prevent it from doing that. So the TEEs, basically, they don't solve everything. You have another option where you could use the TEE to provide a state proof, like for settlement, for example, something like Tyco allows TEE proofs. And that totally works, but it also has to rely on some form of a confirmation of that state. And this TEE proof is only as secure as this confirmation is. All right, so number 7, TEE sequencers don't prevent sequencers from misbehaving, and therefore they really don't actually strengthen a sequencer confirmation. All right, let's see how it does with our definition. So fungible assets, well, sure, if you trust the TEE sequencer, you can do it. Bridge between any two chains, if you trust the sequencer, sure, you can do it. Can you do it fast? Yes. Is it trust minimized? I'm going to say no, because basically it's the same thing as trusting a centralized sequencer, which we generally say is not trust minimized. All right, so confirmations. This is like the key point that all of these things have in common. So this is like the main point, which is that confirmations are the foundation of interoperability. So all interoperability solutions depend on confirmations at some point. And it's just about what is the trust of that confirmation that we have to figure out. But fundamentally, they are the foundation for everything. So we have this trade-off, right? You can have really fast interoperability or really secure interoperability, but you can't have both. And to an extent, yes, that is true. If you want the security of L1 finality, you fundamentally have to wait for L1 finality, and you cannot get faster interop. But I think the point is that this relationship isn't actually linear. It's more of a curve. And I think there's like points over here where you can actually get close to the best. You can get a pretty good compromise between something that's reasonably fast, but also reasonably quite secure. All right, so this is a summary of these harsh truths, but the main takeaway is that confirmations are the foundation of interoperability. All of these other things, TEEs, intends-based sequencing, the L1, they are part of solving interoperability. 100%, they are very useful, but none of them can work without confirmations, and all of these are only as secure as the confirmations backing it. That's the key point. So really, the argument is that we need secure confirmations, or we need to recognize that if our confirmations are insecure, we need to account for that. All right, so that's it. And confirmations are the foundation of interoperability. Thank you.